So we're going to change from diffraction to refraction, two words, again, that sound similar enough that you could get them confused. But refraction is what happens to waves when they cross a media boundary of some sort. Now, different wave media can have different wave velocities due to having different, let's say, elasticities, or maybe there's just different oscillators in one medium than the other. The one that we'll focus on, no pun intended, is light. Light, the speed of light is different in air and in water and in glass and in plastic and so forth. And if you have light passing from air into those media, we have to figure out what changes, what stays the same, and basically what happens. Well, the first thing that we know is that the wave frequency has to stay the same, right? If you have a billion waves per second hitting the surface of the glass, then as it's passing through the interior of the glass, it better still be a billion per second. You can't change that, right? Otherwise, you pile up excess waves somewhere, and there's nowhere for them to go. So the frequency has to stay the same, even if you change to a different medium. That's important to remember. Now, the wave velocity is changing by, our main hypothesis here is we're going from a medium with one velocity to a medium with the other velocity. And as we'll see in the following slide, the wavelength, therefore, has to change in the new medium. Well, you can also see that just from the fact that, lambda f equals v, and if v is changing and f is not changing, lambda has to change, right? So the wavelength is changing inside the medium. It's kind of weird because, if you look at a piece of glass like this beaker, it's clear with respect to light, but in fact, the light slows down when it hits the glass, and inside the glass, the wavelength is different. But you don't see that. You only see the light that came out the other side, which is back to its original wavelength when it emerges. So here's the picture you should have in your head anyway. We have a series of wave crests, plane waves, impinging on the surface, which we'll take to be flat here. And you can see that we have wave crests hitting the surface here, 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 and here. Now, this medium, let's say, has a shorter, let's say a slower speed for light passing through it. Now, this frequency is the same, but in order for the wave crests inside the medium, where light is moving more slowly, to match up at the surface here, 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 and here, it has to be bent. So the light coming in here changes its direction once it gets inside this new medium where it slows down. And it changes just about in the direction that I've indicated here. In fact, you could calculate the direction that it changes. If you know how much it's slowing down here compared to here, you could calculate how much that bending is. And that's what we will use the result of that calculation in a second. So now we're going to change our representation from a whole bunch of plane waves, which is a pain to draw, to just drawing a line, an arrow, a ray indicating the direction of light hitting the surface. And then inside the medium, we'll draw that. You should remember when we draw these rays that it's actually indicating a plane wave both outside and inside the new media. Now, what's actually happening is very difficult to calculate in physics, but we encapsulate it all in what we call the index of refraction, such that the velocity of the set of waves inside the new material is the speed of light in a vacuum divided by n. And usually we reserve n for integers, but in this case, n is not an integer. It's a real number between, it's 1 or greater. For air, n, the index of refraction, n is 1.0029, very, very close to 1. For water, it's about 1.33. Glass, depending on the type of glass, it can vary from 1.5 to 1.6, around in there. Plastic, like the polycarbonate used in most eyeglasses now, has an even higher index, 1.7 something, I believe. And one of the highest known indexes of refraction there is diamond, and that's what gives diamond its brilliance in reflecting light. Light that hits the crystal is cut so that the light bends around and reflects back out, making them very, very shiny crystals. Then you can tell the difference between like cubic zirconium and diamond just by looking at it. Once you know what you're looking for in terms of the brilliance. Anyway. So the velocity is less than whatever the speed of light is in vacuum, which is 3 times 10 to the 8th meters per second. So let's do a clicker question about that. What is the speed of light in glass with an index of refraction of 1.5? And remember that the speed of light in a vacuum is 3 times 10 to the 8th meters per second.